Okay, welcome to our webinar on predicting biogas project gas yield. I'm Paul Green with Green Tech, an RNG project advisory service. I also keep the BioGas TV brand. Today, I'm joined by three friends who you'll enjoy hearing from. First is Eugenio Geraldo, partner with New Organics. Next is Ashwani Kumar, Senior Vice President of Operations with Energia. And finally, Dustin Craig, Bioenergy Practice Leader with CDM Smith. All these are extremely accomplished men in the field of anaerobic digestion and biogas and are leading experts. So the catalyst for this webinar today and the recent article I wrote in Biocycle Connect magazine, it was about the topic of biogas yield where there's not a lot of information around in the public domain. There's not a lot of hard and fast rules on this matter. Information can sometimes be pretty closely held. So I maintain this is a topic that needs further discussion, more transparency, and additional best practice dialogue. Gas yield is a critical part of project success and for process guarantees provided to investors. If this subject is of interest to you and you'd like to be involved in future conversations, please email me. So with that, I'm going to hand the keys over to Dr. Eugenio Geraldo, PhD. He's a partner with New Organics. Eugenio, the floor is yours.
Thank you, Paul. Good afternoon, everyone. Here from New Jersey. Pleasure to be able to share with you some of the experiences on how much biogas through BMP production. So I think you need to give me sharing, Paul. Yep. So I'm Eugenio Giraldo. I'm with New Organics, and we specialize on digestate processing to make nutrient recovery for organic agriculture. You see my email here if you want to contact me. This is what we'll share briefly with you, how to calculate how much methane production. You actually need three things. To quantification of how much organic matter you have there, which is usually a COD or volatile solids. How biodegradable that organic matter is, usually we measure as biochemical methane potential, BMP, and what's the performance of your digester. We'll go over the biochemical methane potential and how we can use it to forecast production, the toxicity assay that is intimately linked to the BMP, and some examples. So the key is to measure that the first part, the organic matter, and usually we measure it through COD or volatile solids. The COD has an advantage because there is a perfect link between the amount of methane that you produce and the COD that is removed. Here you have the COD is usually in organic matter in units of oxygen demand. It could be grams of COD per liter of waste, grams of oxygen per liter of waste, or in a mass basis, grams of oxygen per ton. Some people call it grams of COD per ton. And if you have it and it's fully degraded, you end up with about 90 to 95% of methane and some leftover biomass that grew out of that COD that is there. Methane is a gas and is marginally soluble in water. So when you have it in the digester, that will bubble out of water, and you'll see bubbles of biogas coming out. And that's how the COD is removed. The interesting part with COD that you have a very well-defined number. You know that every gram of COD removed, every kilogram of COD removed, produce 0.35 liters of methane. At standard temperature and pressure of 1 bar and 0 degrees centigrade. This is important to understand that this because it's a gas, you need to specify pressures and temperatures. The biochemical methane potential basically measures the second part, that is the anaerobic biodegradability, and is based on measuring that amount of methane that you produce and linked to the organic matter that you degrade. It is a test that was developed at Stanford University originally around the 1970s. This is the paper that describes, and is a classic in the industry. It describes how to conduct a BMP. And later on, ASTM took that same technique, and with experience of many practitioners, put together an ASTM test method, which is actually called anaerobic biodegradation potential, which links clearly the importance of BMP to define how much biodegradable that organic matter is. It is conducted under strict anaerobic conditions, not limited by nutrients. So you add all the nutrients that the microorganisms might need. Is not toxicity. If there is toxicity, you have to do something to relieve that toxicity of the test, or run it for a long period of time until the toxicity is taken care of. And that's all spelled out here in this both two tests. It is under pH control conditions, so pH is regulated tightly, and you don't have an issue of pH that you usually have in digesters. It's temperature control, so you also have a very stable environment for the microorganisms. You use a broad spectrum inoculum, which means that organisms that are degrading your substrate have the ability of degrade that substrate. And there is strict also procedures to get that inoculum. And you provide enough time for degradation to take place. And when all those conditions are met, then you have your BMP. This is how you conduct it. You first start by making the conditions anaerobic. These are usually, we call serum bottles, about 250 milliliters. You flush the head space to remove any oxygen. And you see here the gas that you use. Specify something between 50 to 70% carbon dioxide to nitrogen. And then you close it after you flush all the head space to remove the oxygen. You incubate it. And usually it doesn't call for mixing, but it is better to mix under temperature control conditions. And then you measure here the amount of biogas that you produce. The original test called for a syringe, and you pull out that biogas. And then you take the biogas and you calculate the amount of methane that is in the biogas, and it plots that over time. This is the original test method. These days, you have at least 2 or 3 different manufacturers that provide automatic measurement of biogas production. And here's one example of them. So you don't have to do it manually. What you obtain is a plot on time on the incubation time, and then the amount of methane that you produce, and it's already on a yield basis. The methane per gram of volatile solids added or gram of COD added. And then each one of these dots represent one of the measurements, and eventually it tapers off and it doesn't produce any more biogas. And in this case, it lasts 70 days. You could see that about 20 days already tapering off, and you could have pretty much, in this case, would be about 300.3 liters, 300 milliliters per gram of volatile solids added. The numbers vary between 200 and 600 in general. One obtains that ultimate yield in terms of methane. And if you do it in terms of COD, liters of CH4 per grams of COD, because the COD has that 1-to-1 relationship of 0.35, say you got 0.3 and theoretically you had 0.35, if all the COD that you added was converted, then you would have a 90% biodegradability. So it gives you, if you do it in terms of COD, it will give you an assessment of that biodegradability in a percentage base. You also get a coefficient of kinetics that some people find it useful. Depending how fast this degradation takes place, you could find and fit to this equation, and this for modelers and for operations might be a useful parameter, and some people find it useful. In order to use the BMP to forecast, we'll go how the BMP is conducted and how the conditions in a digester compares to that, and that will inform us a little bit of the differences. First is nutrient limitations. There's none in the BMP test, but in the digester, you might have some in some cases, nutrient limitations. Sometimes vitamins or trace metals like cobalt might limit. So some companies actually sell a combination of substrates that you could add just to make sure that you don't have any limitations in your digester. The pH control in the BMT is fully buffered, but in the digester you might have impact of pH. Some wastes are not well, especially wastes that have high carbon and low nitrogen, might not be well buffered, and you could have either too low or too high, depending on how you operate it. And you might need to either control the feed or control adding some alkalinity, some chemical control to release the pH. There's no toxicity on the BMT test. You use very small amounts and highly diluted in your test. In your digester, some waste can have toxicity, and that is a common occurrence, especially with some manures and food waste. Potassium can be an issue. Quaternary ammoniums that you have in CIPs, in manures, you might have also some cleaning chemicals and others that impact and can give you toxicity. There's also waste variability. You saw we conduct this in a very small samples, 250 milliliters. It's hard to get a representative sample, especially when you have something as poorly defined as food waste, for example. It has a lot of different components, and you'd have to take something very small and put it in a small bottle. So it could be a challenge, and you would need to define comprehensively sampling and testing campaigns to have representative values. Some waste might have sulfate, especially industrial waste. Sulfate would produce hydrogen sulfide in your reactor, and that decreases the amount of methane that is produced, so reduces the amount of methane production, and also creates toxicity and other problems in biogas upgrading. So you really need to address this one if you have significant amount of sulfate. In co-digestion, usually you saw we test only one sample at a time, but it could be multiple samples substrate tested depending on your campaign and piloting. And you could have antagonistic and synergistic effects. I think later on in the other colleagues will talk about some of those effects. And you basically have an inoculum that's fully acclimated. Sometimes, depending on your waste, the inoculum that they use in the BMP might not be fully acclimated, and while in your digester, acclimation happens de facto. So it is important for the BMP to be representative, to have an inoculum that is acclimated, or to let that test go for long enough to have full degradation. And basically in the digester design, in the BMP, we have ideal condition, but not all digesters are appropriate for all waste. So there is a lot of engineering expertise and piloting that is required to make sure that you'll get full degradation as the BMP says in your digester. So here is just to show that what happens if you don't have a complete digestion. We saw this one before. If we have about 100 of COD and is fully biodegraded, you end up with about 93% of that COD in the methane. And active biomass and residuals of cells would be about the other 7%. This remain in the liquid. This part of the COD ends up in the biogas. And if you have incomplete conversion because there is toxicity or overloads, you will have that some of that COD ends up as residual COD in your effluent and digestate, and then that impacts your yield. So it's clearly important. Toxicity would do that. And that's where the the anaerobic toxicity assay comes about is part of the same paper, 1978 paper from Stanford, the Perry McCarty's group. And this spells out how to conduct the toxicity. Is basically one of the main reasons not to achieve BMP methane yields in your digesters. In manures and food waste that have a lot of proteins, you might see ammonia toxicity. It's very common. Impacts the amount of methane that you produce, impacts the digester design. Some digester designs are better to handle high ammonia than others. You might have long acclimation periods necessary. There's other lists, very comprehensive list of all the types of toxic compounds, and over years people compile those lists, and you know what is toxic and at which concentrations. If you have a suspect that you have toxicity, is worth conducting the EATA test. It will give you the impact on your rates, which would help to design your digester to handle a reduced rate. And also informs co-digestion. All of my colleagues will talk about how when you combine different substrates, you can actually have synergistic effects by diluting some of that toxicity with co-digestion materials. And now we move into some examples where people actually measure the BMPs, and then I went to their digesters and looked if the BMP actually could predict. The references are in the back, all of them, for you to look carefully later. This one is a tomato processing waste. They conducted the BMPs. They looked at using the BMPs, they forecasted the amount of methane produced, and they basically found about 96% of that methane yield that they predicted was observed in the digester. This is a relatively homogeneous and with low variability, so you have all good conditions, no problems. This one is a co-digestion with multiple substrates, is reference 3, that you'll find it in the back. In this case, they have a municipal plant that processes waste activated sludge, and they have a combination of different substrates. They conducted different amount of samples, and you could see, just to give you an idea, for example, for food waste, they took 9 different samples, 5 different BMPs for a total of 45. They found all the parameters here. You could see the numbers are 500, 600 milliliters per or liters per kilogram of volatile solids. Then they took a dynamic model, and they produced this type of example. What you see here shaded is the predicted BMP using a dynamic model. And what you see in a darker is the amount of methane that was predicted, that it was actually measured, excuse me. You'll see high variability, ups and downs, typical of digestive performance. This is measured in weeks. So this is about 6 months worth of data. And you could see the majority of the time, the BMP prediction is above what they actually measured. This graph underneath shows that difference. And when the BMP is high and the prediction is low, you'll have the highest difference. In this case, for example, for 1 week average, they saw up to 25%, but up to 25% difference. Is high variability. So it implies that if you're doing your digester, you want to verify, you need longer periods of time to actually catch the thing on the average that you expect. If you look on average here, they found about 90% of the BMP extrapolation. They actually found it, so all good as well. Second example, same group, but in this case was just green waste and food waste, the same type of graph. But in this case, the difference between the BMP and the actual measurement was significantly higher. If you average all these out, you'll find about 86% of the extrapolated BMP was actually measured as biogas in that digester. And finally, some University of Iowa examples and Cornell. They took 6 different digesters that was doing dairy digesters. They have plug flow and CSTR digesters. And some of them have co-digestion, some of them were just straight dairy. And they looked to BMPs and looked at the actual measurement. Those are the graphs that you see here. The BMP is in light, the digester number is dark, and they put it in a graph comparing the BMP on one end with the digester on the other. And if you look and average this out, they found, again, about 90% of the expected yield from the BMP in the digester. In some cases, though, you'll see here the actual number that you saw in the digester, this case, PATT, you go up Patterson Farms, is a food waste co-digestion. They actually saw more biogas being produced in the digester than the BMP. That happens sometimes. It shows high variability, and that's part of those synergistic effects when you co-digest. As a summary, and we just conclude, the BMP is a standardized test. You find an ASTM that spells out exactly how it should be conducted. There's a lot of experience on how to do this test. There's toxicity effects and that you need to be aware, and the conditions in digestion is not as controlled as BMP, and if you have toxicity, you should be careful with it, as it limits the amount of biogas that you produce. If you don't have toxicity or overloads, you would expect about 90% of the BMP in some cases, there's synergistic effects, and you actually see higher BMPs, that higher yields than the BMP predicts. And finally, the biogas production in digester is dynamic, subject to a lot of variability, and short-term studies for a day or a week, even a few weeks, might give confusing results if you need a longer period of time to average out all those peaks and valleys and have good numbers. And with that, I conclude. Thank you.
Thank you, Eugenio. Appreciate that. BMP is certainly a powerful tool in this space. So I'm going to say a couple of things here, if I can do this right. No, that's not right. You need to stop sharing, Eugenio.
Okay. Make sure I do that. How do I do that?
Okay.
Oh, here's.
You see my screen, Eugenio? Yeah.
Yeah.
Okay.
Stop
Dustin's saying yes, you
got
can
it,
see my screen.
Got it.
Okay.
Sorry.
Okay, so a few kernels of wisdom to share here. So again, I'm Paul Green, and thanks everybody for joining. So I want to make a quick plug for a website I'm working on called BioGas TV. Here's a screenshot. It is in YouTube. So if you go to YouTube, look up BioGas TV. I'm working on getting scientific content on here. So that's where this webinar will go. So let's work on this brand. Everything is free on it. So what resources as an industry do we have to understand gas yield? They're actually precious few. So I find that I've got to resort to European resources sometimes. Like, this is a Swiss report on gas yield where they go through substrate by substrate and they report BMPs. This US paper here, called the Labatut paper, is full of good information on BMPs of various substrates. In Germany, the Bavarian State Ministry of Food has a good website that lists gas yields of different substrates. And I wrote an article this month in Biocycle Connects that's worth a look. It's free. You can read it, on determining RNG performance modeling. So what are some rough rules of thumb for what BMP is. So let's look at dairy manure. So biomethane potential based on volatile solids applied per day. So if you, however much material you're sending to a digester. So BMP, sometimes we speak in terms of methane, sometimes we speak in terms of biogas. So something like Eugenio reported, around 240 liters of methane per kilogram of volatile solids, and somewhere around 400 liters per kilogram of volatile solids of biogas. And so being multilingual here now, we need to be able to talk in imperial units because us Americans like it that way. So about 3.8 cubic feet per pound of VS and maybe 7 cubic feet per pound of VS on biogas. Again, this is from, say, dairy manure. If you look at food wastes, so about 500 liters per kilogram of volatile solids will be your gas yield, give or take. And then on biogas, maybe about 900 liters per kilogram of volatile solids applied. And then in imperial units, somewhere around 7 cubic feet per pound of VS applied and about 13 for biogas. So how to be multilingual in this conversation, right? So imperial units, we're in cubic feet and pounds, and metric, we're in milliliters, liters, tons and grams. But again, your gas yield is either going to be volume of methane or biogas. So when you see BMP presented, quickly ask, okay, is that methane or is that biogas? Because biogas is maybe 55, 60% methane. And the application rate, you're going to have either pounds of volatile solids applied per day or grams or pounds of COD applied per day. So being able to, again, multilingual, we speak about volatile solids, we speak about COD as well. So being multilingual is easy, right? So let's say we want to get 240 liters of methane in metric units over to imperial. First take your kilograms, turn it into pounds, and then you take your liters and you get it to cubic feet. So our 240 liters of methane converts us over to 3.85 cubic feet of methane per pound of VS fed. Easy peasy. So how much biogas comes from digesting a pound of food waste? A very simple sounding question, the answer for which you got to do a bit of digging. So here's the Swedish reference I mentioned to you, page 32, by the way. So they say they have this category, sorted food wastes from restaurants, 27% total solids, 87% volatile solids, 63% methane in the gas. The BMP they report was 506 liters of methane per kilo of VS applied. And so if we convert that to cubic meters of biogas per ton of wet weight, so again, this is volatile solids, but wet weight is different, includes the packaging material and all of your grit and all of your other matter there. So 186 cubic meters per ton of wet weight. And then we can convert that over to imperial. And then finally, this is a good number that's good to remember. So 3.0 cubic feet of biogas per pound of wet feedstock. So I think of a developer that was talking to me the other day. Paul, I've got 100 tons of food waste a day. How much gas is that going to make me? Well, so here's a good number for you. So if you've got a pound of wet feedstock, somewhere around 3 cubic feet of biogas will be your gas yield. So says the Swedish reference. So what tools do we have in our toolbox to talk about our feed and our digester? So volatile solids, VS, total solids, TS. So TS, you dry your material at 200 Fahrenheit. So it's simply drying. But your VS test, you're really cooking it at 1,000 Fahrenheit, burning it down to an ash. So these graphs here, like if you had a sample with this total weight, Your total solids would be this smaller bar. Your volatile solids will be that even smaller bar. And so this is the VS. This can make gas, but not all of it will make gas, because the more challenging solids like cellulose in there, things like in dairy manure, seeing some of the cellulose in that, this is where this area enters the world of imperfection, right? So if this component VS in theory can make gas, but the cellulose needs more time to convert than just the 30 days of a typical digester. There's also this concept of maximum theoretical gas yield. So Eugenio mentioned 0.35 on COD. So 1 pound of COD converted to get that over to imperial units is about 6 cubic feet of methane. As Eugenio reported, in metric, a kilo of COD converted is 0.35 meters of methane created. And so that is all based on stoichiometry, ideal gas behavior, knowing the molecular weights. And once you convert that amount of carbon to methane, those are your theoretical maximums. So you're never going to physically be able to make more gas than that. So you're always going to be somewhat less than that. So there you have it. And I'm going to hand off to Ashwani Kumar from Energia and see if I can find your slides here. Let's see, Ashwani, here we go.
Thank you. Well, I'll start with, I'll go through it quickly, and I'm sure there'll be some questions, so I'll address some of them in the later end. We'll be exploring different methods used by design engineers to estimate the biogas generation potential from different feedstocks. So let's get started. My presentation here may not give you the exact numbers that you're seeing in the other presentation. I believe in the old concept where you give a man a fish and you feed him for a day, but you teach how to fish. And I think that's what I'm trying to do in this presentation in a short span of time. So let's go to the next slide, please. There are always different stages of a project when we develop it. There is a feasibility stage, there is a development stage, there is execution and operation stage of a project. So when you are in a project feasibility or early stages of evaluation, there are ways to theoretically, before a project is considered for serious resource allocation, to realistically estimate the order of magnitude amount of biogas that can be produced from a typical substrate. So there is a desktop projections that we can do based on the feedstock mix or composition of the feedstock. Typically, every feedstock can be broken down into carbohydrates, fats, and protein as a percentage component. And since the anaerobic microorganism during anaerobic decomposition use a very small amount of energy for their own growth, because anaerobic process doesn't generate as much sludge as the aerobic process does. So we will assume that there is no reaction biokinetics loss in it. So based on some of the test and research papers published globally, you can see I pasted a table here in this slide, which kind of give us a fairly good indication on how much biogas can be formed. But please note, this is not a gospel truth. In general, carbohydrates have higher BMP because they are readily biodegradable, but to efficiently convert into, there are different kind of carbohydrates. Say, for example, the BMP or the biomethane potential of glucose, which is a very simple carbohydrates, is as high as 630 to 690 meter cube of methane per kg of volatile solids decomposed. I apologize, I'm using metric terms here. I'm from Canada, so hopefully in the next presentations, I can bring in more imperial methods. Complex carbohydrates like cellulose or hemicellulose have lower BMPs. On the protein side, they obviously have less BMP compared to carbohydrates or fats. They are less biodegradable and they are more resistive to the anaerobic digestion. proteins kind of ranges between 200 to 500 meter cube of methane. However, certain type of proteins such as that can be hydrolyzed more, say for example, ones with higher content of amino acid has higher amount of BMPs. Similarly, fats typically has the most methane and energy content in it, but we always have to be very cautious around how we are dosing fat in a digester and what percentage of the overall composition is the fat component. I have also published here a very simple calculation on how you can estimate the amount of biogas that you can produce from a ton of food waste with some constants here. I'm sure this slide will be available so in the video, so we can go through it. We can go to the next slide. During the project development stage, and I think we all have talked about BMP or biochemical methane potential, this is kind of a validation test for a feedstock. It gives us a more accurate method to evaluate the amount of biogas a feedstock can generate. But there's a lot of confusion around BMP in terms of you send the same sample to different labs and you will get different BMP results. Sometimes different sample collected from the same feedstock in different seasons or different age also gives you different kind of BMPs. There's a lot of discussion around it, but there are a couple of reasons for these variances, and we have to understand it as design engineers. What are those variances and why are they coming our way? BMP obviously needs a set of skills to prepare the assay bottles, identify the right kind of media. It is done in a very controlled environment of a lab, basically. We also make sure while we are doing it, we are controlling all kind of toxicity. We're dosing the right kind of pH. We are making sure we are adding the right kind of nutrients and the micronutrients. And that may not happen in a real scale plant. We have to be very aware of this. Some labs also use internally cultivated seed or inoculum or the biomass. And there's always a risk that the seed inoculum may not be exactly conducive to the kind of inoculum that we are looking for. So we always have to watch out for this. And we also make sure that we understand that it's a validation tool, and it doesn't necessarily mean that whatever we get in a BMP test is the kind of numbers we should use in our financial modeling. Conventionally, as design engineer, I have always used 85% of my theoretical BMP as my design values or performance values when it comes to developing a financial performer in a project at this stage. Making the right recipe and using the standardized inoculum all across is key. We have to understand that sampling of feedstock is done right, and we are not being knocked down because of seasonality or age of the feedstock or how we are sampling and stuff like that. Next slide, please. So during the project financing stage, this is the stage where we need to be very, very accurate. And this is where a couple of things come together. It's like different tributaries comes and forms a river, basically. There is an empirical model, which is basically based on characterization of feedstock. We know what the organic content is. We know this by measuring the total solids and the volatile solids of the feedstock. We know its pH, nutrient composition, we can estimate, we know its source. So based on all this, we can estimate the biogas generation potential. These models often use couple of lab experiments, couple of feed samples. So you need some site walks to be done, followed by the benchtop studies. BMP is typically a benchtop. And then most of the technology providers, we do develop a very, very reliable models to estimate biogas that comes with years and years of data collection and experience around it. Then once we have it from different plants, we put all that experience into simple tables and format, and we get a validation from a benchtop study or a small pilot study. And all this, it comes together. So we start with substrate analysis, we do some desktop estimation, we validate the BMPs, we try to do a pilot if possible. But we also get all these tests reviewed by an experienced engineer who has operating experience and who have the luxury of having a database from different years of operating different plants and stuff like that. So that's how ultimately it comes to conclusion. Thank you, Paul. Next slide. Co-digestion is something we have seen as that seems to be, co-digestion improves, there's synergetic effects of co-digestion, and there's a lot of studies which are published. The theme of my slide, I think you can read through it, but the theme is there is a theoretical BMP, say for example, of biosolids, and there is a theoretical BMP for fat, oil, and grease. But if you combine the two and co-digest it, the net biogas that this co-digestion or combined feedstock will generate will be more than the arithmetic addition of these two BMPs. And the reason for that is because the co-digestion brings in that different kind of microorganisms that are more resistive, they're more forgiving, they're more compatible to different feedstocks. There is improved nutrient balance, and there is also a resistance to fight inhibitions, and it creates that increased diversity of microorganisms. Next slide, please. The operations is important. Like, we can get BMPs in the lab, but once the plant is in the operational stage, the amount of biogas that we can recover, there are a plethora of variables and factors that affect biogas recovery from a particular feedstock. It can be as simple as, if the feed is fresh, do we have all the volatile solids available that can decompose? Is it aged? Is the feedstock sitting outside for a while and it has lost a degradable VS? Seasonality plays a major role. Say, for example, during holiday periods, there is high probability that we get feedstock which is rich in proteins on food waste digesters, say, for example. There is also factors such as digester operations, the pH, the temperature, the alkalinity, the nutrients. Are we sticking to the right feed regimen, basically? Are we feeding or starving the digesters and feeding everything in batches? There's different ways. What is the partial pressure? We can talk at length. Are we feeding too much fat, oil, and greases in it? What is the right residence time? Are we maintaining the right temperature and others in it? So there are several operational parameters and factors that affect the biogas recovery of a substrate in aerobic digesters, including something like organic loading rates, hydraulic residence times, temperatures, pH. Nutrient is an important factor and most ignored one most of the times. Compared to our nutrients requirement for anaerobic digester, typically for nitrogen, phosphorus, and sulfur is 10:2:1. That's a thumb rule I normally use for every 100 milligrams of biomass, because that's where it is used. If you want to go on a more concentration basis, typically it is 50 to 10 to 5 milligrams per liter in it. On the micronutrient side, ferrous, cobalt, and nickel, these are sometimes zinc also get added, are key components, and we have to test and add them. We also have to make sure that all the mixers and digesters are, we are mixing it properly and maintaining the right kind of agitation that is required in the digester. Next slide, please. Inhibiting substances, I think this has been talked at length. Obviously, the outcome of this is, let me tell you why this is important. Now, we have to watch out for ammonia, which comes from protein sources, and ammonia can be fairly toxic. Similarly, we also have to watch out for sulfur in the digesters, but one thing we always watch out for is the volatile fatty acid. And they are basically acetic acid, propionic acid, and butyric acid. We want this to be in the range of 60:20:20, or even better, 17:15:15. As we see the acetic acid ratio reducing, we know digester is moving in the wrong direction. VFAs are the first indication that the digester is healthy or not. And we have to keep an eye on it for maximizing our biogas recovery or maintaining it as close as possible to our BMP values. So I think we can read through it otherwise. Paul, next slide, please. Thank you. You have my phone and email. Just in case you have any questions, don't hesitate to reach out to me. Thank you.
Okay, we've got Dustin Craig from CDM Smith with us here now. Take it away.
All right, you guys can hear me okay, right?
Yeah, gotcha.
All right. Okay, so I'm kind of wrapping this up here. We might be running a little bit long here, so I'm going to cruise through some of these. Have two case studies I want to talk about that are really leading the way in co-digestion. So these are both operating facilities, similar but different. So I wanted to highlight and see co-digestion in operation. The first is the Greater Lords Sanitation District. Next slide. Oh, well, before we get to that, actually, here is the most common path to receiving this food waste for municipal facilities, I'll say. Oftentimes is, you have food waste generators, cafeterias, and so forth. That will be source separated and sent to a pre-processing facility, sometimes through a separate stream or sometimes combined and pulled out of the municipal solid waste. And then it's processed and then trucked to a water reclamation facility. So this is the most common method we see for a lot of traditional food waste. And really what it's about is turning this giant heap of rotting vegetables into an actual very useful feed slurry into digestion. So who would think that we're looking at energy right there? But we are. And that's what we're working to harness that energy. So an example of that energy is on the left picture here, and it's that slurry, not very appetizing looking, but it is very appetizing to our anaerobic bugs and digesters. So typically the offloading station, the material is slurried up to 9–10%, as high as you can get it and still get it off the truck. It's pumped off the truck into a receiving tank, and then we like to mix up those tanks and make sure we're keeping that a homogeneous blend, and then slowly feed that into our digester process. So that is a generic, typical organic waste receiving system. Next. So now we want to get to GLSD, Greater Lawrence Sanitation District, a great case study, about a 50 MGD facility in Massachusetts. That really has a cutting edge co-digestion and food waste diversion program. So we'll get a little bit into the details here. So back, probably 2014 timeframe or so, the state of Massachusetts was passing organics diversion legislation, and their landfills were filling up. They knew that all of this food waste was a pretty sizable greenhouse gas emission source. The landfills, landfills don't do a great job of capturing that gas, and there's always methane leakage. So they started to implement organics diversion. And what that led to is really a push to find out, well, where can we take this? You can take it to composting, or even better, you can take it to a digestion facility. And that led the way for an initial feasibility study at the facility to look and see, well, how much of this source separated organics could we receive? About 28,000 gallons per day in their existing system. But if we added a fourth digester, we could bump that up significantly and really be a good host for all this organic diversion to achieve the organic diversion legislation goals. And with the addition of that, of course, you're going to produce a whole lot more energy. So that legislation is what led to this program. Next. So here's the pure data of what that full-scale pilot and full-scale startup operation really looked like on the SSO feed. So you can see the biogas production humming along, let's say 450 SCFM. And then in the blue, we start to add in our source separated organics. And the right axis is how much gallons per day we're feeding in. So not a tremendous amount of waste from a volume basis, say 20,000, even 25,000 gallons per day. You can see the direct impact that had on the overall system gas production. So significant increases in gas production, and just speaks to how volatile or feedstock this food slurry was. Next. So the project ultimately went down the CHP path and installed 3.2 megawatts of capacity. They have a very unique net metering agreement. And it was a little painful to get through that agreement, but we got there, where they have an off-site lift station. Their influent lift station is just a little bit off-site. It's really just down the street, and there's a significant power demand there. So we work through utility and are able to net meter so that we can put power back on the grid, only to pull it off down the street for the big influent pump station, the RSPS. So a little bit of unique aspect on this system, but that net metering comes into play a little bit later. Naturally, we're recovering the heat there. Here's an overall picture of the facility. See that nice shiny digester on the left-hand side. We've got our gas treatment, siloxanes, and H2S as well. The CHP is in that building closest, and then we have all of our emissions equipment up there on the roof to meet some very stringent air emission requirements. A great job with the pointer, Paul.
Thank you, Dustin. You know, I'm pretty good at some things.
So this is this is average yearly data. So you're looking at a whole bunch of data here, just averaged out over, let's see, 5 years. So what this indicates is that net metering agreement, and you can see on the overall net zero operation, we started to meet that where the blue goes actually negative. And that's just a testament to all of the energy that this facility is bringing in the form of source separated organics and the net metering agreement. But they would have never got there if they weren't able to bring in additional waste, produce that energy, and put that power back on the grid to offset their usage at the RSPS, and then actually have some extra net metering power. Okay, so that's one case study, looking at time here. Moving to the center of the country and the Des Moines Wastewater Reclamation Authority. This is a regional facility, serves basically the entire area of Des Moines, and I've had the privilege to work with them for a number of years. This, I will say, is the second largest co-digestion program in the US on a municipal scale, at least that I know of, I think behind East Bay Mud. They don't get as much publicity. They kind of have that Midwest modesty and maybe fly under the radar a little bit, but they received 20,000 plus loads of hauled in organic waste from 90 different customers in 2019. That's actually grown a little bit over the last couple of years as well. So just a significant program that they've built up over decades, really. So it's just a traditional wastewater treatment, primary and secondary treatment, and naturally anaerobic digestion. The unique aspect is this program where they bring in all this high strength waste, and Iowa's kind of the heartland, and they're doing a whole lot of food processing there. So they benefit from having a lot of these feedstocks within their collection area and even beyond the entire state of Iowa. But they're bringing in about 50% of their total volatile solids loading to the digesters is coming in via this high strength hauled waste. And it produces a tremendous amount of biogas. They use that for process heating, building heating. They do have some power generation that is mostly offline. They were selling gas to an industrial user. They no longer do that. And they've gone all in on renewable natural gas, which we'll get to. So just an example of their organic waste receiving facility. They can receive 3 trucks at a time. They drop down to a below grade tank there that's 140,000 gallons. That tank is well mixed, and then that is slowly bled into the digestion process. So they're receiving 50, 60, 70 trucks per day through this facility. It's a really humming operation coming through here. And there's often a little bit of a line waiting to offload some waste. So the first phase of this project goes back quite a ways to 2009 to 2014, and we really took those digesters and fixed some of the issues they had with handling all this high-strength waste. We put new submerged fixed concrete covers on them. They kind of mimic the operation of an egg-shaped digester in the traditional pancake style configuration, so a little bit better scum and foam control. New mixing, new gas conveyance. We improved that hauled waste receiving facility that we saw in the last picture. And the overall goal is really design a more resilient process and facility to handle this tremendous amount of hauled waste and the high amount of biogas that it was producing. Next slide. And here's just a picture of that finished submerged fixed concrete cover. On 5 of the primaries, we are running that gas membrane digester there as a secondary digester, a little wide spot in the line for both the biogas system and the sludge level fluctuations there for dewatering. But they have a tremendous amount of digestion capacity. Each of these tanks is about 3 million gallons. So big digesters, and they receive a whole lot of outside waste to those. Uh-oh.
Yeah, what's going on here?
It's running away from you. There we go.
You here?
There we go. Perfect. So this, again, this is data that looks at 11 years of data here. And you can see the blue is their biogas production. And then the green is their volatile solids loading on an average basis per day. So you can see right about that line where the digester project was completed. You can see the dramatic increase in biogas production and a more modest increase in volatile solids loading. And really that's the result of going from a limited mixing system of only about 500 GPM to 62,000 GPM. So about 125-fold increase in the mixing energy going into these digesters. Mixing everything together, making sure there's no dead zones, and really distributing that heat and optimizing the reactor is what we attribute to that big increase in biogas production. That created a new problem, which they started flaring gas again. So they got their digester process up and running and producing more gas, and then they only to turn around and flare more gas, which everybody hates. Nobody likes to burn that biogas. So that led to the next phase of the project, which was a renewable natural gas project. And we installed a 2250 SCFM capacity pressure swing absorption system here. And what we were doing, of course, is to optimize the production of this biogas, create RNG, put it in the pipeline, and get some return on our investment. So it is generating about $6.5 million a year in gross revenue right now through that. A little bit on the pipeline spec versus the digester gas. We had a great pipeline spec. I think sometimes not everybody is as beneficial of this. That 0.3% oxygen is nice, and we've never had any issues with that. We've been very low on oxygen, but it's nice to have a little breathing room on your oxygen criteria, because a PSA system and most gas processing systems don't do much to remove oxygen. Other than that, we've had no problems meeting those pipeline requirements. Little pictures of the site. These cogen engines had reached the end of their useful life, and we needed this space, so we cleared them out. Next picture. So we had to do some extensive modifications in this room, tear everything up, cut holes in the wall, make it explosion proof for class 1 div 1 for the gas processing system. And then here is the finished room looking from that same vantage point of our pressure swing absorption system. Whole lot of stainless steel piping, lot of mechanical equipment, but has been running very well and producing high quality renewable natural gas. Next slide. I just got some more pictures. Who doesn't love all this stainless steel piping and mechanical equipment? That's a 700 horsepower feed compressor there on the left. So the wrap up of this is this is a very successful co-digestion program, and it's been built over decades and decades through WRA's vision. They're receiving quite a bit of money just from organic waste tipping fees of receiving this waste. Then they're turning around and producing renewable energy and generating more money off of that. Payback for this system is tracking, it's actually under 4 to 5 years is the latest numbers I've seen. And they've got a lot of good publicity. And actually, it was really cool. The EPA administrator, Michael Regan, visited the site about a year and a half ago and took a tour just to see what all they're going on during COVID times. You can see with the masks. So all in all, great project. And really an example of what co-digestion can do at a very large scale.
Cool.
So that's my contact. How are we on time, Paul?
Beautiful. Thank you. I appreciate you picking up a few minutes there. So thanks. Thank you, Dustin. We are at time. So we're going to go take the questions now. We got some questions coming in, and we'll go until 1/4 the hour and then call it good at that. So due to a technical glitch, you all may not get an email from me tomorrow. So if you want a copy of the slides, get your pencil out. You may have this from me earlier, green.tech.llc@gmail, green.tech. So send me an email, green.tech.llc@gmail if you want a copy of these slides. So this is great. This is all about teaching, learning, sharing, open spirit of collaboration. I'm going to keep going with some of this technical content. The next webinar is May 9th on pre-processing, grinding, maceration of food waste. So stay tuned. And if anybody attendee here has a topic that you think would be pertinent, these webinars are so easy to do. They're free. They're no cost to anybody. So with that, let's try to take a couple of questions here. So let's see. What is the impact on RNG pricing, market value with substrate addition? Ashwani, you want to try to take that? So substrate addition on RNG pricing. So clearly your RIN changes from a D3 cellulosic to a D5 advanced biogas RIN. Anything else on that? It's really that.
No, I'll stick to that. Like, I think I can take the other ones if you're okay with that. Like,
yeah. Can you see the screen here? Let's see.
Yeah, I can speak to that. It's a big bummer, in my opinion, that bringing in these additional feedstock then devalues the RIN values. I believe you can separate out the feedstocks and run sort of parallel digestion systems and then meter that gas and then feed it into a common gas upgrading system. That has been, folks have followed that pathway, but that's not an ideal way to feed your digesters. So it definitely has a big impact and maybe perhaps drives some of these co-digestion to RNG programs more into the voluntary market, which is Des Moines.
Question on the tip fee per gallon at Des Moines, Dustin?
Yeah, that they have a pretty complex tipping fee on that I'm not able to share kind of overall. They do have different tiers of costs they essentially subsidize some of the fog developed within their collection facility. So they have a very low tipping fee for that. They want that out of the sewer and they want that to be brought to them. So they feel like, we should have a very low fee for that. And then some of the other feedstocks have a higher tipping fee outside their collection area. I think there's a little bit of info on their website that's publicly available for that question. It's Des Moines WRA, you search.
So a question from Lisa Chang here on without co-digestion, is there a rule of thumb how many cubic feet of biogas you could make per MGD of influent? That's a good one. So the BMP of biosolids is, can we make that conversion on the fly? Cubic feet of gas per MGD of influent? That's a tricky one. I'll let you guys noodle on that one.
Yeah,
do-
I
Go
was
ahead.
gonna say, it's tough to make some biogas projects pencil out for below 10 MGD. And there's a lot of factors that go into that. Whether they have digestion now, cost of electricity, RNG values, if they do have these outside organic waste, strength of wastewater, all these factors. But there is a lot of economy of scale on these systems. So it just gets a little tougher the smaller the system is.
And we also have to understand what kind of biosolid we are talking about. Is it thickened? Is it dewatered? How is it coming to us? Is it a primary biosolids, or what is the ratio of primary and secondary? So I know we were looking for thumb rules, but it's complicated to give away these thumb rules without understanding some more details around it. But long story short, if you know your TS average coming in and you know your ratios of primary and secondary, you can ballpark assume 70% of it is volatile solids. And you can use a BMP of 650, I'm talking metric again, on the primary, and you can use 400 on the secondary and do theoretical calculations around it. How much biogas you will make. Assume 60% methane, 10 kilowatt per nm cube of methane calorific value, and then you can convert into RNG or CHP, whatever route you want to go. So sorry, I'm giving a lot of numbers away, but it's a calculation you have to do based on your case studies.
So I like this question. It's a thoughtful, deep one. So when do you look at total versus soluble COD as question part A? And then part B is, how well does VS correlate with COD for different feedstocks?
I can take a first stab at it and feel free to jump in. Typically use soluble COD when you're trying to understand, mostly in aerobic treatment plant. In a industrial waste treatment plant, COD is the norm that you use, especially around high strength anaerobic digester, fixed film anaerobic digester, USB digester, CSTRs, which have residence time of 9 days. COD is a more soluble form of organic. At the end of the day, we are trying to understand how much is the biodegradable organics in there. There are multiple ways to understand it. You can use a COD, you can use a BOD number, you can use a volatile solid number. But conventionally, COD is more used in a high strength anaerobic digester space for solid waste digesters, be it a manure digesters or biosolid digesters or food waste digesters. Volatile solids are a lot more convenient to do on the field for operators to day-to-day correlate the biogas with the volatile solids they are getting. Again, there's plethora of things that can change even within the volatile solids, but it's a more accurate method too. Like it's hard to I don't know how many of us in this are from the lab, but just the pipette and the tube and the hole through which you suck a sample in, it will be extremely difficult to do COD of a solid waste sample. And if somebody does it, then it will be inaccurate because the homogeneity of it is extremely difficult. Whereas on a VS, it's extremely consistent day after day. So VS is a more accurate measure to understand the amount of organic matter that is available or coming to us. So that's kind of the basis of why solid waste digesters go with VS and why high strength soluble liquid digesters go with COD. Conventionally, for anaerobic digester point of view, you would like to consider the total COD and not the soluble COD. Soluble COD you only need in the aerobic treatment side when you have to go in the denitrification space and you want to compare your organic availability to denitrify, but that's the only space I've seen it used.
Question here on gas upgrading successes. So what has been working? What do we see out there in the market for gas upgrading techniques that have been succeeding? I know, Dustin, you're at that PSA at Des Moines. That works pretty well, doesn't it?
Yeah, it works well. Produces high quality RNG. We've never had a problem meeting the performance, the pipeline injection specifications. but it's mechanically intense, right? You saw those pictures. There's a lot going on, a lot of horsepower draw, and it has a pretty low methane capture compared to other technologies that we're losing about 5 to 7% of the methane out the tail gas, which is a bummer. That has to get oxidized in a thermal oxidizer. So there's always advantages and disadvantages on all these systems, depends on the scale. I would probably venture to say that membrane systems are probably growing in popularity. I don't know, Ashwani, if you're shaking your head.
Yeah, I can vouch for that. Like,
yeah,
obviously, yeah. PSA do work, and water scrubbing has been there conventionally, and but more and more of the projects it's a function of cost benefit in which region and what is the methane purity expectations in the pipeline. But if you have to meet so-called biomethane kind of quality, membrane separation is gaining more traction there. Where you use a permeable membrane and selectively remove impurities from the raw biogas. Of course, there is some pre-treatment before this, ammonia recovery and activated carbons and stuff like that. But membrane separation is it's gaining more tractions more and more, especially in the US and North America side. But there are other technologies, PSA and water scrubbing, which are also fairly successful. But again, the watch out is always what is the methane concentration and impurities that you're looking for in the pipeline, and then go back and select the technology.
Yeah, and amine scrubbing too, as well as out there.
So with that, I'm going to thank my friends, speakers that joined. This was by no means a holistic review. It was more meant to be provocative and to trigger further conversations. So Dustin, Eugenio, Ashwani, thank you for your time. Thanks to all the guests that joined. And stay tuned for more of these webinars. With that, we'll call it a wrap. So thanks, guys.
Thank you so much.
Thanks, everybody.